Hi everyone, this is my second video regarding work energy power. If you haven't watched my first video, which I have explained all the theory parts in this lesson and the first worked example, it's better if you can watch that video first and refer this one later. For this video, I have selected 2002 A-level pass paper, Applied Mathematics, question number 2, section B. The question is, a train of total mass 300 metric tons is traveling at a constant speed of 54 kilometers per hour on a straight level track, and the total resistance to the motion is 50 Newton per metric ton. So the most important thing given in the question is the train is traveling at a constant speed. Constant speed is 54 kilometers per hour. So we have to convert this into meters per second. 54 multiplied by 1000 divided by 60 twice. So the answer is 15 meters per second. So this is the velocity in meters per second. If I sketch the train engine, the mass is 300 metric ton. Ton is 1000 kilogram. It is 300 into 1000 in kilograms. Traction force given by the engine is P. Then the resistance is given 50 Newton per metric ton. So train engine is having a total of 300 metric ton. So 300 into 50 will be the total resistance, 50 Newton per metric ton. Entire mass is 300 metric tons. So the total resistance is total mass into 50, 300 into 50. Now we can apply our equation H equals PV. Power of the train engine is equivalent to the product of traction force into velocity. Since the train is moving under constant velocity from Newton's second law, we know that the train is in equilibrium. Therefore, P is equivalent to this resistance. There is no acceleration, constant speed, no acceleration. Train engine is in equilibrium. Therefore, P is equivalent to this resistance force. 300 into 50 is the total resistance. Velocity is 15. We have 3 zeros. 3 times 5, 15. 15 into 15 is 225. This is a power, so it is given in watt. I can use kilowatt instead of 3 zeros. So this is the power of the engine. Second part of that question, the rear coach of mass 50 metric tons then gets disconnected, but the tractive force of the engine is unaltered. So earlier the train engine exerted a power of 225 kilowatt. Now its rear coach of mass 50 metric tons got disconnected. Now the new mass dragged by the engine is 250. Earlier the total mass was 300. 300 minus 50, the disconnected mass is 250, 10 to the power 3 kilogram. Now the resistance is also changed. because resistance was given as 50 Newton per metric ton. Now the mass is 250. So 250 into 50 will be the total resistance, new resistance. But P force, tractive force, is not changed. Then we have to calculate the acceleration of the train. Since the force applied is not changed, but the mass got changed, the train is not in equilibrium. There is an unbalanced force. Due to that, it will accelerate. Now we have to apply F equals ma forward. Total forward force is given by the engine, which is equivalent to 15,000. Because initial traction force was 15,000. Minus, now there is a resistance of 250 into 50. Traction force not changed. Earlier traction force was equivalent to 15,000. So this is from part 1. Equal to mass is 250 into 10 to the power 3 into acceleration. From this we can calculate the acceleration. This is 15,000 minus 25 into 5, 125, and we have two zeros, 12,500. This is 250,000. And we have A, the difference is 2,500 divided by 250,000. It is 1 over 1000, which is equivalent to 0.01. Two zeros got cancelled. Here it is 100, not 1000. So it is 1 over 100, 0.01 meters per second square is the acceleration. Then Roman number 2, we have to calculate the distance moved by the disconnected coach before coming to rest. So there is a short method to get this answer. In theory video I explained, when we do a work we have to spend energy. Similarly, the rear coach is having a resistance. So this is the rear coach. Mass is 50 metric ton. So the total resistance for this rear coach is 50 into 50. Resistance force is going to decelerate the rear coach. Therefore, the total work done by this resistance force is equivalent to the loss of kinetic energy of the rear coach. Loss of kinetic energy, delta, should be delta EK, is equivalent to work done by this resistance force. Kinetic energy is half into mass into velocity squared. Mass of the coach is 50 into 1000. Velocity, change of velocity, is 15 minus 0. Why? Initially the train was traveling at a speed of 54 kilometers per hour, which we converted into meters per second. It was 15. Now we have to find the distance moved by the disconnected coach before coming to rest. That means when it reaches zero velocity. So change is 15. 15 minus 0, 15. So 15 square equals work done. So work done is equivalent to displacement into applied force. So applied force is the resistance force into moved distance, S. Now we can simplify. 50 times 1, 50 times 1, then 0, 0 get cancelled, 2 times 1, 2 times 50, 5 times 1, 5 times 10. So S will be 15 square 225 into 10. So moved distance is 2250 meters. Once again I repeat, the theory used here is work done is equivalent to change of kinetic energy. So that concludes my second video on work energy power. Thank you.